Hello everybody. In this video, we're going to use method of consistent deformation to solve the reactions and the internal forces of a statically indeterminate structure. This structure has a fixed support at point A. So at point A, we have vertical force, horizontal force, and the bending moment. At point C, we have a roller support, so there is a vertical force pointing upward. The total number of reactions or unknown is 4, but we can only write 3 equilibrium equations, so there is 1 redundant reaction. Let's assume this one redundant reaction is from point C. Based on the superposition law, the indeterminate beam we have here, it equals to situation 1 plus situation 2. In situation 1, we only have the external force, P, applied at point B. In situation 2, we have the reaction force applied at point C, right? So there are 2 loading conditions applied on the same structure, which is a cantilever beam fixed at point A. Another way to understand this is to assume that we don't have any forces at point C. So when we apply external load at point B, there will be some deflection at point C. But if there were some support reaction at point C, the force at point C will reduce the deflection at point C, right? So if I use delta CO to represent the deflection at point C caused by the external force P, I'll use delta CC to represent deflection at point C caused by the reaction force C. If we have a situation where delta CO plus delta CC equals 0, that would be equivalent to the original indeterminate beam where we have in the beginning. Right, so let's first look at what will happen when we have an external force but no reaction at point C. So this is a statically determinate structure. We can calculate all the reactions first. So AX is 0, AY is 32K, and MA will be 320 kPa foot. If I plot the bending moment, it will be something look like this. 320. This is point load, this is B, this is C, this is A. This will be a negative bending moment, right? Because the top of the beam is under tension, bottom of the beam is under compression. So this will be a negative bending moment. Now I'm interested in the deflection at point C caused by this external force. I'm going to solve it using conjugate beam method. When I use conjugate beam method, I'm going to apply M over EI as the distributed load. So this will be 320 over EI. Because this is a negative bending, I'm going to apply the distributed load pointing downward. I will calculate the bending at point C. The bending at point C from this conjugate beam will be the deflection at point C from the original beam. So this MJ is 320 over EI. That's the area of this triangle. Multiply the moment arm, 2/3 multiply 10. This is the first 10 feet plus the second 10 feet. I'll get 26,666 over EI. In this example, E is 30,000 KSI. I is 512 inch to the power of 4. So deflection I have, the delta is 3 inch. The deflection should be downward. But let's look at how we can get that conclusion from conjugate beam method. So for the MG, we know G has to be clockwise, right, to balance the load here. And when we talk about positive beam bending moment, we know that only when the bending moment makes a bow shape, it is a positive bending. In this case, what we have for the MG, it's in the opposite direction, right? So it's a negative bending. Therefore, delta should be pointing downward. Now let's focus on the reaction at point C. So in this case, we have an upward force at point C to bend the beam back to where it's supposed to be. Let's say there is a situation where an engineer built a cantilever beam, there is no support at point C, and then later they found that the deflection at point C is quite large, so they decided to put a support back to this beam. So what is the force in that support so that they can bend the beam back to where it's supposed to be? I'm going to call the deflection here as delta cc. So that's a deflection at point C caused by the force at point C. And the force I'm going to apply is just 1 kPa, because I don't know how much force I need to apply, right? So I just apply a unit force. If I apply unit force, then the bending moment, it should look like this. So that's 20. The length of this beam is 20 feet. And now I'm interested in the deflection at point C. Because I'm applying a unit force, I'm going to call the deflection from the unit force as FCC. This is also called the flexibility coefficient. So here, the FCC is a deflection at point C caused by 1 unit load. I'm going to use moment area method to calculate deflection. The area of this bending moment diagram is 20 times 20 times half. And I also need the distance from the centroid of this triangle to point C. So this will be 2/3 of 20 meters. And in the end, everything needs to be divided by EI. If I do this calculation, it should be 2666 over EI. And plug in EI value, this should be 0.3 inch. So in this case, we will have 0.3 inch deflection upward for every unit load I apply at point C. Just now, we know that from the external force applied at point B, the downward deflection is 3 inch. So to reduce the deflection to 0 at point C, the force I'm going to apply should be 10 kPa, right? If I apply 10 kPa of force, that will be 3 inch deflection upward, then delta cc plus delta co would be 0. So what we have here is cy multiply the flexibility coefficient. This equals to delta cc. Cy is a force, so the unit could be just in kPa. And FCC is the deflection per force. So I'll just make it inch per kPa. And deflection, the unit of deflection here will just be inch, right? So another way to write the compatibility equation here will be delta C. This is a reality, equals delta CO plus delta CC. That has to be 0. because delta CC equals CY times FCC, then what we will have here is CY equals minus delta CO over FCC. Okay, that's it for this video.